you have to say Anantalakshmi introduced before me.
You are too famous. It's a pleasure to introduce Professor Anantalakshmi, my colleague from Hyderabad and a good friend, a quantum optics person who does theory and very close to experiment. And we have written papers together. I have a lot of respect for her as a teacher, as a researcher. So it's only a pleasure that he is introducing Professor Gautam Vemuri, who is also a very close friend of her, and also I know him quite well by now. Thank you.
Okay, Prashanta, thank you. I asked for it. And it is indeed a pleasure for me to introduce Professor Gautam Vemuri. Gautam is an old friend. I have known him since 1993. And not getting into, the amount of time we have spent at the university during various visits of Gautam, let me briefly introduce you to Professor Gautam Vemuri to the audience. Professor Gautam Vemuri has, obtained his degree in physics honors from St. Stephen's College in 1984. And then he did his MSc in 1986 from Brown University. Then later on, he went on to do his PhD at the Georgia Institute of Technology, Atlanta. Then later, he served as a postdoc at Gila, University of Colorado for 2 years, 1990 to 92. Then he obtained a faculty position at IUPUI, and he's been there at that university ever since. And he has been a professor at the IUPUI for a very long time, for more than 2.5 decades. And in fact, from 2002 to 2009, he served as the chair of the department. And coming to his research interests are mainly in the areas of laser physics and nonlinear optics, with a special emphasis on stochastic and nonlinear dynamical behavior of optical systems. And some of the honors which to the credit of Professor Gautam Vemuri are, he served on the editorial board of various journals, so some of them which I will mention here. He was on the editorial board of Optics Communications for about 2 decades. And he has been on the editorial board of Research Letters in Physics since 2007, and on the editorial board of Pramana since 2013. And he's also served as a member of the executive committee of the American Physical Society Prairie section in 2009. And Dr. Vemuri has also served as special editor of special issues of Optics Communications, which was devoted to optics in the life sciences. And also Professor Gautam Vemuri has been named the senior member of Optical Society of America. Professor Gautam Vemuri has visited University of Hyderabad several times. And he has, each time the topic on which he delivered a lecture was entirely different from the previous one. He has works in very many areas which are, very interesting and current. I now, over to Professor Gautam Vemuri. Today he is going to talk to us about the delay-coupled semiconductor lasers as a platform for PT-symmetry. Over to Professor Gautam Vemuri.
Thank you so much, Anantalakshmi. Wow, that was quite an introduction. There should be some rule that the time taken to introduce a speaker should be shorter than the lecture itself. But in any case, it's wonderful to see old friends. Anantalakshmi, as she has said, is an old friend. I could not say no to an invitation from Professor Panigrahi. Prashanta and I go back a long way. So I thought I was told that this is a session on parity time symmetry. So, we have dabbled in this area. And so I thought I would share with you today what it is that we're doing. So let me share my screen first. And let me find my laser pointer here. Okay, so here's the title, Delay-Coupled Semiconductor Lasers as a Platform for Parity Time Symmetry. And this work is done in collaboration with a couple of students, Joe Sulzer, who graduated about 4 years ago and is now employed at the US Air Force Base in Dayton, and then Andrew Wilkie, who recently got his PhD and is now a postdoc at the University of Southern California. And our theoretical conscience is my colleague, Professor Yogesh Joglekar, who first got me introduced to this whole field of parity time symmetry. Now, it's possible that you have heard a lot of talks on parity time symmetry. So let me just take one slide to just sort of introduce what is sort of the very basic ideas. And the interest in this whole field of PT-symmetry stems from this paper, almost 25, 30 years ago by Carl Bender, which said that a non-Hermitian Hamiltonian may have a real spectrum if it is simultaneously parity and time reversal symmetric. And what the parity operator does is it changes the sign of the position and the momentum, and the time reversal operator changes the sign of the complex I so it changes I to the negative I. And the interest in this parity time symmetry was originally to understand to develop a framework for the quantum mechanics of open systems, which is where these non-Hermitian Hamiltonians arise. So anytime you have dissipation in a system, which is, any real system would have dissipation, then one has these non-Hermitian Hamiltonians. Several applications have since been proposed of these parity time symmetric systems, which include non-reciprocal propagation of light, the development of single mode lasers, spontaneous generation of photons, and so on. And in recent years, there's been a lot of interest in something called exceptional points of these systems. Now, exceptional points there's nothing inherently quantum mechanical about them. They are just properties of non-Hermitian matrices. And what an exceptional point is, you have an exceptional point when the eigenvalues are degenerate, but not only are the eigenvalues degenerate, but the corresponding eigenvectors are also degenerate. So if the eigenvectors are parallel to each other and the corresponding eigenvalues are degenerate, we say we have an exceptional point. And this is just a general property of non-Hermitian matrices, but they have some very interesting applications as well as properties. So that's one of the focus areas these days for a lot of people who work in the field of parity time symmetry. Now, in order to set what we are doing with semiconductor lasers in some sort of a context, let me go back and sort of just briefly review what is a very basic paradigm in this field of parity time symmetry. And that is, let us assume that we have two waveguides, so let's just assume we have a chip which consists of two waveguides that are coupled to each other. And one of these waveguides amplifies light. So at a rate, the gain is given by gamma. And then there's another waveguide which attenuates light at the same rate. And then as light and the direction of propagation of light is as shown by this arrow. So I put some light in at the top, it goes through. But then there's these two waveguides are coupled to each other. So light can couple back and forth at some rate J. Now this system can be described by an effective, essentially a classical equation, which is given here, where if you think of E1 and E2 as the electric fields that are put into these two waveguides. You can sort of easily understand that, for example, if there's no coupling, so you set the off-diagonal element 0, you would see that E1 dot, that the electric field 1 is amplified in the first channel and it's attenuated in the second channel. On the other hand, if you set gamma equal to 0, so you set the gain and loss terms equal to 0, but leave J, then of course you just get exchange of energy between these two waveguides. But this equation that I've written here is very similar to the Schrodinger equation, which is, so if you see there's this sort of one-to-one, and this arises because the Schrodinger equation is, after all, is just a wave equation. And so, as is this one here. And so we can think of this, so people think of this as, if you think of this as a quantum system, then this is the equation of motion for that. Now, so the effective Hamiltonian is given by this. You can see it is obviously non-Hermitian. If you apply the parity operator, you interchange the diagonal elements. So gain goes to loss and loss goes to gain. But then if you apply the time reversal operator, you change the sign of the complex I. And so by simultaneously applying both the P and the T operators, you recover the original Hamiltonian. Now this Hamiltonian has eigenvalues, which are given by this quantity here. And so these eigenvalues can be real or complex, depending upon the relative values of the coupling term J and this gain loss term, which is gamma. And people refer to this point where gamma is equal to J as the PT-symmetric threshold, or sort of the transition point. So what happens at this transition point? So I show you here the total. So I put some light in here, and then it sort of couples back and forth, and I put a detector at this end, and I measure the total intensity of light that comes out here. And if I plot that as a function of time, this n equals 2 refers to having just 2 waveguides. You can see that gamma is less than J, so the eigenvalues for this system would be real. Then what one gets is bounded oscillations in the total intensity. On the other hand, if gamma exceeds J, you can see that the eigenvalues become complex. And so now the total intensity as a function of time exponentially blows up. You can see that this vertical axis is 10 to the power 13. So this transition, when the eigenvalues go from real to complex, this is a signature of parity times symmetry. So the behavior of the total intensity, or the norm of the wave function, goes from bounded to unbounded. Now, one can also plot what this total intensity looks as a function of this gain loss term. So this is normalized to the coupling rate. It should have been J, but think of that kappa as this coupling rate J. And then, of course, you see that the intensity stays bounded, and then eventually, when gamma exceeds the coupling rate, you get this exponential blow-up. So when I talk about our experiments and our work on semiconductor lasers, these are the kind of pictures I will show you of what happens to the norm of the wave function as a function of the gamma, the diagonal term, which some people also refer to as the non-hermiticity parameter. So with that background, let me talk briefly about what is a semiconductor laser. A semiconductor laser is, the ones that we use are made of aluminum gallium arsenide. It effectively consists of a P-type semiconductor and an N-type semiconductor, which are fused together. And then you apply some bias voltage, you put some current. So the P-type carriers move down, the N moves up. They recombine in this area, which is called the depletion region. Now, this entire thing is the laser itself. It's a chip where the back end is highly reflective and acts as a mirror. The front end is partially reflective. And so that acts like an output coupler. And so light bounces back and forth. The P and N type carriers combine here, release some energy. That energy bounces back and forth. Some of it comes out in the form of laser light. The dimensions of this system are on the orders of this dimension is about 100 to 150 microns. This is also on the orders of about 100 microns, and the depth is about 50 microns. So these are fairly small chips. These are also fairly inexpensive lasers, and they're very, very robust. You can run them for 3,000 to 5,000 hours off just a single battery. So they're very robust. Now, these lasers have some interesting properties which we make use of in order to implement parity times symmetry, and I will refer to those properties at the appropriate time. Now, for many years, I was working on nonlinear dynamics of these lasers, and one of the things about these semiconductor lasers, they're also called laser diodes, so you'll occasionally see me calling them LDs, is that they're very, very sensitive to feedback of light. And there's various types of feedback. There's light coming out of the laser, hits the mirror, goes back in. It's also possible that instead of a mirror, if you have a grating, then the light that goes back is spectrally filtered. I show that here in a different form. If this is just a plain mirror and then you have a Fabry-Perot-Etalon, then the light that is fed back into the laser is, instead of the entire spectrum being fed back, it is spectrally filtered. That's referred to as filtered optical feedback. We've done some work where this mirror is a phase conjugate mirror. So there's all these various different types of feedback mechanisms. Some of the properties, some of these common features of these various feedbacks are that because these semiconductor lasers have very high gain, these lasers are very sensitive to external perturbations, unlike sort of other lasers that you might be familiar with. And that sensitivity then leads to instabilities in the laser dynamics and leads to all kinds of complicated behaviors, including chaos. So people who use semiconductor lasers go to great trouble to avoid any feedback. And what we are going to do is, when I talk about our work, is we're going to actually deliberately inject light into these lasers. So we're going to have to contend with this chaos, and we do it in a rather simple way that I'll tell you here. These lasers have, this feedback has a lot of applications. Over the years, people have worked designing all optical components for signal processing, synchronized chaotic oscillators. Hold on a second, something happened to my, sorry, my computer, some window popped up, I had to get rid of it. Okay, so for random number generation through the hardware using the chaotic properties. So all of these things are features of feedback. So the model that we use is, so here's get my laser pointer back. Okay, so here's my semiconductor laser, and let's just say I have some optical elements here. It could be something as simple as a mirror, and so light comes out of the mirror. It hits these optical elements, and some part of it gets fed back into the laser. And the round trip time it takes for this is, let's call that tau. Now, these equations I have written here are sort of the standard semiconductor laser rate equations, where E is the electric field, that is the intracavity field, and N is the carrier inversion. P is the pumping. This alpha, this is called the line width enhancement factor, and this is a material property of the semiconductor laser that arises from the fact that the gain spectrum of a semiconductor laser is asymmetric about resonance. Now, this feedback is included in this term here, where kappa is the fraction of light that's coupled back in. T minus tau, that is the delayed feedback, because the light that comes out of this laser hits this and goes back in. So at any given instant, the electric field inside the laser is affected by an electric field that came out of the laser a round trip time tau before. Okay, so that's where this comes from. And then this e to the I theta times tau, this is the phase accumulation factor, because if the light comes out of the laser and goes back in, then there is an extra accumulated phase here, where this theta times tau is that accumulated phase factor. Now this T here, this is the ratio of the lifetimes of N to E. P is a pumping term. And then this piece here accounts for gain saturation. As you can see, it's nonlinear. Now this delay term here makes this entire system of equations infinite dimensional. One way to recognize that it is infinite dimensional is to recognize that the electric field at any time T depends upon the entire history of what the electric field was during a round trip time tau before. So if you want to know what the electric field is at time T, you have to feed the entire history before that, which then gives you an infinite hierarchy of equations for this electric field. And so that makes the system infinite dimensional and then makes it analytically intractable. So what is the effect of this feedback? So let me for a moment set this kappa equal to 0. So there's no feedback, just have a solitary semiconductor laser. And here's my electric field equation, my equation for the carrier inversion. I plot the intensity as a function of time. And so I see this relaxation oscillations, and then the laser intensity goes to a steady state. This is the carrier inversion. So this is N, it's just out of phase because the energy due to relaxation oscillations is being exchanged between the E and the N. And so you get this behavior. And now here I turn on the feedback. And so now you can see that the intensity starts to behave. And this is in fact a manifestation of chaos. So please note the horizontal scale. This picture here with no feedback for the intensity is only up to about 4 times 10 to the 4 picoseconds. This one starts at 6 times 10 to the 4 picoseconds. So where this has settled to a steady state, this one in the presence of feedback still has lots of dynamics that are going on in it, which can complicate things. Okay, so one of the things I want you to remember then is that this feedback can cause a lot of instabilities in the output of the laser. Okay, with that brief background on what happens to a semiconductor laser when there is feedback, let me now turn to the topic at hand, which is how to use these coupled semiconductor lasers to create a platform for parity time symmetry. Now, the motivation for our doing this is, I told you about this example with the waveguides, but there are many other platforms that people use for implementing PT-symmetry. Many of them depend upon having to make gain equal to loss, which is usually quite difficult to do because loss is something that is passively present in a system, but gain requires external pumping. And so to match these two to be exactly equal is quite difficult. Assuming one has done that, the other difficulty is if you want to do an experiment with different levels of coupling, this off-diagonal element of the Hamiltonian, then every time one has to fabricate a new system. It's not quite easy to continuously vary this coupling. So most of the experiments that have been implemented to date have required precisely fabricated systems. Our goal, and in most things I've done, is can I implement this in an off-the-shelf components? Can I just buy some very simple things and put them together? And can I do it that way? And finally, what is the effect of this time delay, which is inherent to these semiconductor lasers because of the nature of the characteristic timescales in the laser? So this was our motivation. So what we do is we take two semiconductor lasers, which are identical in all respects, and we operate them at slightly different frequencies, one of them at omega-1, the other one at omega-2. So there is a small detuning between them. And we just couple them into each other. So that's the feedback aspect. And then we monitor the intensity of each one. So these two lasers then are the analogs of the two waveguides. And that, sort of the picture I showed you before. And then let us see what happens with this. So these are the rate equations now that I just showed you, but now modified for the two lasers. So the subscripts 1 and 2 refer to the two lasers. There is an additional detuning term that appears because laser 1 sees a detuning of omega-1 minus omega-2, but laser 2 sees a detuning which is exactly of the opposite sign. It sees omega-2 minus omega-1. And here is the coupling term. E1 is coupled to a delayed E2. E2 is coupled to a delayed E1. These equations are written in a frame that is rotating at the average frequency of the two lasers. So at omega-1 plus omega-2 divided by 2. And so this theta then is the average of the two frequencies. And it's a phase accumulation factor which plays an important role. So if you look at this, this is the model for the coupled semiconductor lasers. This is sort of the paradigmatic model for what people use for a PT dimer. And there's, of course, no similarity between the two. This is what the semiconductor lasers, it's a completely classical rate equation model. It has got nonlinearities, it has got gain saturation, it's got detunings, it's got phase accumulations, it's got time delay. So it's a really, really messy system with lots of moving parts. And is there any reason to think that this system of equations behaves anything like this? So in order to motivate that, yes, this could look like this, let's make a few approximations. So I have taken these first two equations and written them in matrix form. So this is exactly the same. And now I'll make two assumptions. One, I'll say, okay, let us for the moment assume that the time delay is 0. Okay, even though it's physically unrealistic, let us for a moment say, okay, I'll set this tau equal to 0. The other physically realistic assumption I will make is that for any laser, once it is operating in the steady state, the carrier inversion goes to 0, which means N1 and N2 can be set equal to 0. So I set N1 to equal to 0, I set the tau equal to 0, and this equation, this matrix here, this effective Hamiltonian reduces to this. Now you can compare this to what I derived for the waveguides, and you can see that they're very similar. Kappa is the same, it's the coupling between the two systems. The difference now is instead of having gain and loss, what I have is a plus I delta omega minus I delta omega, where delta omega is the relative detuning between the two lasers. And one of the criticisms of this waveguide model was that it's hard to make the gain and loss equal to each other. In this system, the gain and loss are always automatically equal to each other because laser 1 sees omega-1 minus omega-2. Laser 2 will then automatically see the opposite of that. And so the diagonal elements are always equal to each other. Plus, it's not really a gain and a loss, it's just a detuning. Now, strictly speaking, this is what is called an anti-PT symmetric system, but this is a detail that we need not stress about too much here. So of course it's parity time symmetric. It's a non-Hermitian Hamiltonian. It satisfies the requirements for PT-symmetry just like this one does. It has eigenvalues which are given by which are real or imaginary depending upon the relative values of the coupling and the frequency detuning. Okay, great. So just to summarize, what's the difference between the waveguide model versus the lasers? The laser model is a time-delayed system because the separation between the two lasers is on the orders of about a meter, which corresponds to about 3 nanoseconds. The characteristic timescales of the lasers are usually a sub-nanosecond to picoseconds. And so therefore, this extra time it takes for light to travel from one laser to another cannot be ignored. The laser model is a classical system. It uses rate equations instead of the Schrodinger equation. So it's missing the I that's in front of the Schrodinger equation. It's missing. It's a longitudinal coupling. With the waveguides, the coupling of light is transfers to the direction of the propagation of the light. In the case of the lasers, it's longitudinal coupling. I've already mentioned that the gain loss term in the waveguides is replaced by frequency detuning, which is always equal to each other. And the nice thing about the laser model is that the detuning can be very easily controlled by changing some parameters like temperature and pump current. But more importantly, the off-diagonal elements, which is the coupling of light from one laser to another, is also very easily controlled by just putting a neutral density filter and rotating that. The final piece is this phase accumulation factor. I won't talk about it much today, but it's an extra degree of freedom. Remember that phase accumulation term depends upon the product of theta times tau. Theta is the average frequency of the lasers, which is easily changeable, and tau, which is the separation between the lasers, is also within one's control. So there's lots of extra degrees of freedom, lots of moving parts that one can use to study this system. So this is just the experimental design. The only thing I want to stress here is that the way we change the relative detuning between the two lasers is by holding the temperature of one of the lasers fixed and then varying the temperature of the other laser. And when you change the temperature, you change the refractive index, which then changes the frequency of the laser. Okay, so this non-hermiticity parameter is changed by scanning the frequency of one laser. Okay, so let's see what happens. So here is my reduced model. So this is after I made all those approximations by setting the time delay equal to 0, by setting the carrier inversion equal to 0. I did all of those things. I look at the real part and the imaginary part of the eigenvalues as a function of delta omega. I get these very characteristic behaviors that some of you may be familiar with. Now this picture, this is the intensity of each laser. So there are actually two curves here, the red one and the blue one. And this is the detuning between the lasers. This picture here is obtained for zero detuning by numerically simulating those 4 rate equations I showed you. So now when I simulate those 4 rate equations, it's the complete model. It includes the nonlinearities, includes the pumping. So it includes all of those factors in it. And what you find is that when the eigenvalues are complex, the intensity stays bounded, which is this very rapidly varying blue here. But then this vertical green line, this is where kappa equals delta omega. In this case, it's on the orders of 0.1 in scaled units. If you want to convert any of my scaled units to real units, you just multiply it by 100 gigahertz. So in this case, this picture goes from negative 30 gigahertz to plus 30 gigahertz. And precisely this, when kappa equals delta omega, which is the PT threshold, what that rate equation model is predicting, that you get this abrupt jump in the intensity, which is characteristic of a PT transition. And then on the other side of resonance, you get a very similar behavior. Now, I want to stress that this abrupt increase in intensity is not due to some resonance-like effect. The gain bandwidth of these semiconductor lasers is very, very wide. It's on the orders of about 100 to 300 gigahertz. So on this scale, the gain is pretty much flat. So what one is seeing here is truly an effect of this PT transition, where you get an abrupt change in the intensity. So in this regime, the eigenvalues are real, and out here, the eigenvalues are complex. So when you get this transition from complex to real eigenvalues, you get this sudden jump. But this is, of course, simulated with zero delay. But what happens in the presence of a time delay? That's the question we're really interested in. So this picture is I've just repeated the same picture I just showed you. One of the things I want to stress is that in the experiments, we are not able to measure this rapidly oscillating blue here. So we do a time average over about 10 nanoseconds. So this red curve here, this is the time averaged out here in the wings. Okay, that's the time average over a 10 nanosecond detector. Okay, this is the picture that you get for the eigenvalues and the intensities if you include the time delay. So now I have a time delay, but I'm still neglecting the phase factor, so that e to the I theta tau, I set that artificially equal to 1. Okay, so but you get a very dramatic change in the real part of the eigenvalue. You still get the central dome, which corresponds to this piece here. But in addition, out in the wings, you get all these transitions. Look at the fact that they're changing in sign. Okay, so these are not oscillations as much as they are truly additional transitions that arise in an infinite dimensional system. As soon as you make tau non-zero, you have an infinite dimensional system. And the signature of that is that you get all these additional transitions, which are flipping sign. Then you get the central dome, which is analogous to this. Down here, so this is done by numerically solving this. And again, you can see that that if you look at the eigenvalues of this, you'll get a transcendental equation because this lambda is inside the matrix. And so therefore, it's an infinite dimensional system. Down here, this is done with the full set of 4 rate equations. And now the red and the blue, they correspond to 2 different lasers, but I'm plotting the time averaged intensity. So I've detector averaged intensity. So these oscillations out in the wings are not the same as these fast oscillating blue. In the presence, you should be comparing these oscillations to this flat red line. So as soon as one has a time delay, one gets these. Again, this vertical line, this is where the PT transition is. You get this big jump and then oscillations out in the wings. Finally, if I include the phase factor, okay, which I had neglected in this middle panel, if I include that, then you find that there are 2 major changes. One, the horizontal axis is the same, by the way, for all these figures. You get these transitions become much more quicker. You still have the central dome. But the other thing you get is an asymmetry. So let's follow this blue curve, for example, out here. You see all these transitions out in the wings. Then you get this big central dome. Then out here, the blue curve just becomes flat. Okay, there's no oscillations. If you look at the red, if you start from the right-hand side, it undergoes all these transitions. You get to the central dome, and then it flattens out. So now if I go to those 4 rate equations, the full model with the nonlinearities and everything in it, you see a faithful reproduction of this. You get, if you follow the, if you follow these along, you get the sideband oscillations, which are much faster than the ones out here, and then you get the central dome. Okay, so even with the time delay, the features of parity time symmetry, principally this very abrupt jump in the intensity at the PT transition, that is still preserved in this completely classical rate equation model, which is much more messy than this very simple, 2x2 matrix. Okay, so fine, this is all predicted by the simulations. What about what happens when you actually start to look at an experiment? So the way to look at this slide is to each column here corresponds to a particular time delay. This L is the spacing between the 2 lasers, which you can then, you can do C over L, and you get what the time delay is. The time delay here is stated in scaled units. Everything is scaled to 10 picoseconds, which is the photon lifetime. So the top row here, this is the real and the imaginary parts of the eigenvalues derived after this simplification of the rate equations down to by setting the inversion equal to 0. The middle panel here is what you get from solving the entire set of 4 rate equations, so it is simulations. Then the bottom panel is the experimental results. So let me go to this middle section here for a moment to point out a few things. As one increases the delay, one finds that the sideband oscillations, which are the signature of a time delay, those become faster and they diminish in amplitude. And that the central dome is always preserved at the PT transition. If I look at the experiments now, again, I have 2 lasers, so that's why I have 2 curves. You will find that if you look at these oscillations, they diminish in amplitude as you increase the time delay, and their frequency becomes, and the transitions become much, much quicker. So this is a convincing proof that this pair of coupled semiconductor lasers, even with a time delay, they seem to retain many of the features of an otherwise, sort of the standard parity time symmetric system. So because our system is one with a time delay, and the signature of that time delay is the sideband oscillations, I'm going to focus on some properties of those oscillations. Now, when I first introduced this, the rate equation model, I told you that it's analytically intractable, and that has generally been true. I have been working with these rate equation models for more than 20 years. I'd never known anybody to solve them analytically. But then a couple of years ago, in the context of our working with this parity time symmetry, my colleague Joe Glaker, discovered something called the Lambert W function. I mean, he did not discover the function itself. That's known for many years. But he discovered the utility of this in solving equations of this kind, which have a time delay in them. I won't go through all the details of how one uses the Lambert W function. We have put the details in a conference proceedings that you can look up if you're interested. But the Lambert W function, under appropriate conditions, can be used to solve these rate equations that we are using. So we tried to see what are some of the predictions that we could make analytically and see how they stand up to scrutiny with the full numerical model and with experiments. So there were some important predictions that we were able to make analytically using this Lambert W function. The first was that this dome width, and by dome width, I mean this distance here. Remember, this transition, this point at which the intensity abruptly increases, that is where that is the PT transition. And the same thing is true on the other side. So the distance between, the separation between these two, we refer to that as the dome width. Now, in a conventional parity time symmetric system, as you increase the diagonal element, so let's say I increase delta omega, then, so if I increase delta omega, so let's say I move to the left, then the change in this abrupt change in intensity would happen at a point, it would also move to the left. And so therefore, and this one would move to the right. And so the dome width would just monotonically increase in a standard system. What our system does, and at least our prediction is that it varies discontinuously as you change the delay. The second prediction we were able to make is that these secondary transitions, the ones out in the wings, we can predict at what frequency they occur. That is, what is the frequency at which the sign of the eigenvalue changes. Number two, that these oscillations, the secondary transitions, their frequency is independent of the coupling strength, and that it is linearly dependent on the inverse of the delay. So let's see how these manifest themselves. So here I just reproduce this as a visual guide for you. When I say sideband oscillations, I mean these things out here on the side, and we say that the sideband oscillation width is independent of the coupling strength, and that the width is inversely proportional to the delay time. So here is a picture of what, it sort of includes the experiments, the numerical simulations, and everything in it. So what we're plotting is the sideband oscillation width as a function of the inverse of the delay. So these black squares here, this is what we get from the full numerical model. And so so you can see that it varies linearly with 1/tau. These colored markers here, these are the experimental measurements. And these different colors refer to different values of the coupling strength. And so if you look at these different values of 1/tau, so if you look at these different places, so if you look here at these 4 points, if you look at these 3 here, you look at these 3 here, you can see that the colors are all scrambled, which means that it doesn't matter what the coupling is, okay? You get more or less the same value for the sideband oscillation width. That's point number one, that the width is independent of the coupling strength. The fact that the width is inversely proportional to the delay time, you can see from this straight line. Now, the fact that this experimental measurements don't quite sit on what the numerical model or the analytic results predict has to do with with how we change the delta omega, how we change the detuning, and how the detuning is not independent of the phase accumulation factor in our experiments, because that theta itself depends on delta omega, and that's what gives rise to this discrepancy. So the slope here should be pi over 2. That's what is analytically predicted, and that is what is found from the rate equation model. But this slope, the experimental slope, is about 20% off from that, and we understand why that happens. Okay, the second prediction we have is that the sideband oscillation amplitude, that is, what is the amplitude of the sideband oscillations, that is inversely proportional to the oscillation number n. So we number the sideband oscillations as oscillation number 1, 2, 3, so on. And then we predict that from the Lambert W function that the amplitude is inversely proportional to the oscillation number. So then we go to the full rate equation model and we do that and we find, sure enough, yes, it's linear. So this is numerical simulations. We also predict that the sideband oscillation amplitude, you can see that it is decaying and that the decay rate is proportional to this dimensionless quantity kappa, which is the coupling rate, and tau, which is the delay. We do this numerically. This is all numerical simulations. We do this for two different cases. One, this PA stands for phase accumulation, that e to the I theta tau. First, we set the phase accumulation equal to 0. We find that this linear relationship is preserved. Then we do it for the variable phase accumulation, which is what happens in our experiment. And we find that, sure enough, the numerical simulations predict that you still get a linear behavior with a different slope. This is all simulations. Now, what about experiments? So here is the experiment for what is the amplitude as a function of the sideband oscillation. The experimental data, you can see it's quite linear. Now, the decay rate of the amplitude of the oscillations is a function of kappa tau. It's linear up to some point, up to kappa tau equals about 2 or so, and then it flattens out. And we're not quite sure why this happens. So this is one area where I'm not able to, at the moment, quite explain why. So if you look at the numerical simulations, kappa tau all the way from 0 to about 5 or 10, the numerical simulations predict that it's a straight line, but the experiments then tend to, the decay rate tends to flatten out. And so this is a discrepancy that we still have to figure out why that happens. Okay, so let me go to this dome width. I told you that one of the predictions we can make is that the dome width increases non-monotonically. So here this is, for the 0 delay. So that's my definition of what the dome width is. In the case of 0 delay, the dome width would just increase monotonically with kappa tau. Whereas if I have with delay, I get this more complicated behavior. So what we do is we plot this dome width, which is just the separation between these two in some, in dimensionless units. So we divide by kappa, and then we plot that as a function of kappa tau. So this is, just think of this as the dome width, this picture. This dotted line, that is without the phase accumulation. So it's a bit of a toy model. And the solid line is with the phase accumulation. And you can see that just as it would happen for the 0 delay, there is an overall increase in the dome width, but it is not a monotonic increase. There are all these discontinuous transitions that happen. So in other words, this width here would vary discontinuously as a function of kappa tau. So this is the same picture reproduced here, but here is the numerical simulation for, so this is with the 4 rate equations. And you can see that the dome width as a function of kappa tau, it more or less closely matches what one predicts from analytically. So, for at the kappa tau equal to 1, there's a transition. Well, there's a peak at kappa tau equal to 1. At kappa tau equal to about 2.5 is the next peak. So here at about 2.5 is the next peak. Then the next one is at 3.5. Here it is at 3.5, and so on. And then when we do this, so this is the analytic prediction. This is from the full numerical model. And then here is the experimental result. And again, you can see that there's a big jump at around kappa tau equals 1. There's another jump at about 2.5, then at about 3 or so, 3.5, and then it sort of flattens out and saturates out here. Okay, so the experiment also reproduces what is predicted numerically and analytically. Okay, finally, let me turn to this idea of what are of exceptional points in this time-delayed system. I have defined the exceptional points previously as this is when you have a simultaneous degeneracy in both the eigenvalues and the corresponding eigenvectors. They're important in the context of parity time symmetry because these PT transitions are usually occur at an exceptional point. So here is again for the zero delay, the simplest case, the real part of the eigenvalue. So right here, when kappa equals gamma is an exceptional point, the real part and the imaginary part of the eigenvalues. So the question then is, what kind of exceptional points arise in our time-delayed system? So we start with the effective Hamiltonian. So this is, this matrix here. This is my effective Hamiltonian. Okay, fine. You can write down what the characteristic equation looks like. You can see that it is transcendental because here's a lambda. Here's again lambda, which is the eigenvalue. So so you kind of have to do this, solve this graphically. It's difficult to solve them analytically. So we again go back to our Lambert W function, and we try to determine, sort of predict analytically what happens. So the way we approach this is we say, okay, I have this characteristic equation, and I'm going to flip this around, and I'm going to solve this for those critical detunings for which there exists a degeneracy. But remember, there are an infinite number of eigenvalues here, but the only eigenvalues that matter are the two largest ones, because it's the two largest ones that contribute to what the intensities of these lasers, how the intensities would behave. So we solve analytically for those critical detunings for which there is a pair of degenerate eigenvalues. And the expression ends up looking like this, where here is the Lambert W function. Okay, so we do this for a large number of values of kappa tau. And what we get is a picture like this, where this vertical axis here is this critical detuning delta omega c, which is what this is. So again, just to remind you, this is the value of the detuning for which you get degenerate eigenvalues. And then we sweep kappa tau here. And what you get is two distinct curves. This one, the curve A, which is at delta omega over kappa equal to 1. So that is where one would expect the conventional PT transition to occur. So up to a kappa tau of about from 0 to 0.4 or so, you just get the conventional PT transitions. So you get the conventional exceptional points. So that's what this is. When kappa tau is less than 0.4, you get one exceptional point near what is the traditional one. But then between 0.4 and 0.5, which is this curve B, this is the region in which you get, so you can kind of see that there are, if you pick any slice here, there are two exceptional point curves, okay? And then once you get beyond 0.5, then you get these isolated exceptional points here for certain values of kappa tau. Now, what is interesting about this exceptional point behavior is that this is a dimer, so we expect the exceptional points to be of order 2. And yes, sure enough, you get second order exceptional points in the system. But right here at the cusp, where curves A and B meet, you get what is called a third order exceptional point. A third order exceptional point is one in which 3 eigenvalues and the corresponding 3 eigenvectors become degenerate. So a system that is infinite dimensional is able to produce so it's an infinite dimensional system with 2 components in it. It's got 2 lasers in it. If there was no time delay, then these 2 laser system would produce exceptional points which are of second order. In the absence of any time delay, if you have 3 lasers, you would get a third order exceptional point. If you go to 4 lasers, fourth order exceptional point, so on. This is all in the absence of a time delay. In the presence of a time delay, because there are an infinite number of exceptional eigenvalues, our expectation was that we would find exceptional points of an infinite order. But that's not quite what happens. You get exceptional points either of second order, and you get one exceptional point, which is of a third order. So that's what's in the bold here, that all exceptional points are second order, with the exception of just one exceptional point right here at the cusp where A and B meet, which is a third order cusp. And we check this numerically, and we confirm that these results are true. So let me summarize here by saying that non-Hermitian Hamiltonian. This is the first line is just the standard definition of what is a parity time symmetric system. Can have a non-Hermitian Hamiltonian can have real eigenvalues. What we find is that the signatures of PT-symmetry are actually quite robust. They persist in the presence of time-delayed coupling, nonlinearities in the laser system that arise from the saturation of the gain medium. I haven't talked much about noise, but the real experimental system is going to have quantum noise, which is quite large in semiconductor lasers. But these features persist in the presence of, these PT-symmetry features persist in the presence of all these complications. The delayed coupling introduces new features in the PT-symmetric behavior. In particular, the dome width now varies discontinuously. And then we get these sideband transitions, which have properties which we are able to faithfully predict, both analytically and numerically. It's a rather versatile system because it allows the control of important parameters. In particular with the phase accumulation factor e to the I theta tau, because that comes with kappa, the system offers the possibility of making the coupling real or complex just by varying either theta or tau. We have developed an analytic description of the system using the Lambert W function, and we find that in general there is good agreement between the theory, the simulations, and the experiments. And with that, I thank you for your attention, and I'm happy to answer any questions you might have.
Sarah,
Yes,
maybe?
Professor. Prashant, you want to say something?
No, please go ahead. Please go ahead.
Actually, Gautam, that was a very informative talk. A complex problem. You have really made it, simplified it, and explained it in such a way that all of us can understand. I was just wondering, because there are a large number of students here, probably if you suggest some applications of this, foreseeable applications are already existing, so where it is being used, maybe that will bring in more excitement into the minds of the students. So is it possible for you to elaborate on some application points?
Right. So I think the whole a system that is parity time symmetric, at least to me, the most interesting part of that is really the time reversal part of it. Because in optics, most things are time reversal symmetric. So, if you think of a piece of glass, you put some light through that piece of glass, the light going, it goes forward, and when it comes backward, the behavior is the same. So it's temporally the behavior is symmetric. When you break this time reversal symmetry, what you do is the behavior is non-reciprocal. And this, for students, they may be familiar with what happens to light in the presence of a magnetic field. So for example, the optical Faraday effect, which is used, to make isolators. So the optical Faraday effect is where. Sorry, did somebody have? I heard somebody. Okay, so the optical Faraday effect is where the polarization of light is rotated by a magnetic field. So anytime you have a magnetic field, you break the symmetry. So any applications that you can think of where you break this reciprocal behavior of light is interesting. So it can be it can be used for cloaking and things of that sort. Now, in our specific experiment where we have this sideband oscillations as a function of delta omega. Okay, so it's not sort of these oscillations are not in the time domain, but these oscillations are actually as a function of something in the frequency space. This, we have not done it yet, but we can think of some potential applications in, for example, looking at systems which have an inhomogeneous refractive index, for example. You're really looking for something that whereas light propagates through a medium, if there's a change in the frequency of light, then you can imagine a surface which is inhomogeneous in refractive index. So let's just say I have a two-dimensional flat surface which is inhomogeneous in its refractive index. And so when you run light through it, if it's a PT-symmetric material, or if I'm operating at one of these transition points in the sideband oscillations, then I can get these very rapid changes in the intensity as a function of frequency. And so I can use that to map the inhomogeneous refractive index of the surface.
Very
so
interesting.
these are somewhat speculative. I have to grant that. I think I'm actually not aware yet of anybody using these to make using anything in parity times symmetry to make a device.
Thank you. And there are a few questions from the chat box. I will read it to you. There is one question. Is there any way to realize a 3-level system in PT-symmetric Hamiltonians?
Oh, yes. Yeah. I mean, so I showed you the waveguide example and I showed you the coupled lasers. You can have, for example, 3 waveguides, so three coupled lasers. Okay, so let me stick to the laser model since that was what my talk was about. You can imagine having 3 lasers, which are all coupled to each other. In the simplest case, in the absence of a time delay, the effective Hamiltonian would now have the diagonal elements would be I delta omega 0 and negative I delta omega. So the one that's in the laser has a certain reference frequency. So let's call that laser number 2. Laser number 1 would be detuned by delta omega from laser number 1. And laser number 3 would be detuned by negative delta omega from the central laser. That's a 3-level system. So in principle, one can have essentially an infinite lattice. Okay, so this need not be a finite system.
Can I ask a question here?
Yes, please.
Yeah, sorry, go ahead.
Yeah, just very curious. I think this the n-level system which you mentioned is indeed interesting. That's exactly one thing which I was thinking about. That when you said nth order exceptional point, that essentially amounts to an n cross n matrix whose eigen states are becoming degenerate and eigen functions are collapsing, and so let me just pause there. So I think that's exactly like, spin n in a large spin in a magnetic field. Imagine that you have posed a spin in a magnetic field where the spin has 2s plus 1 state. And for a Hermitian system, that would be equivalent to saying that slowly I tune my magnetic field to 0, where all the spin projection states are degenerate, right? Now this is a non-Hermitian version of that, with the exception that all the eigenstates are now 1, not n. So now, when I'm thinking of a mapping, this is the mapping which comes to my mind. But
yes.
but as far as the eigenstates are concerned, the information there is about electric field. So what was not clear to me, once you're tuned to the exceptional point, what exactly is happening to the electric field physically? Is it becoming parallel because of the 2 lasers, or they are at an angle, or what are they doing? What is this collapse?
What is happening to the eigen functions? Is that what you were asking?
Yes, and they have implications for the electric field themselves, physically.
Yeah. Well, okay, so that's a much more, okay, so the first part is easy to answer, that the eigenvectors are becoming parallel to each other.
Yes, that I understand.
Now, what is happening to the electric field is actually a much more complicated answer. So let me just share my screen for a second so I can, and that has to do in part with how complicated the system itself is. But let me just pull up the appropriate slide to shed some light on this. So, but let me preface what I'm going to say by just saying that, so what we measure or what we calculate is we calculate the norm of the wave function. So in this case, we calculate the intensity. Okay, so we're calculating E star E, even though the whole model is in terms of E. Okay?
Yeah, right.
And so therefore, when we ask this question, what is happening to the electric field? The answer is I don't know. And the reason I don't know is the following. So can you see my screen and this figure?
Yeah, absolutely.
Okay.
Yeah, I can see it.
So remember I pointed out this asymmetry that, let's just focus on this red curve for a minute. It oscillates on the right, but it stays flat on the left. Okay.
Yeah.
And then the blue does the opposite. But look at what happens when I calculate when I use the full laser model. You don't quite see that. If I look at laser 1, and let's say red is laser 1, it oscillates on both sides. Okay? And laser 2, and so in this picture, laser 1 is the one who's detuning. I'm continuously changing. So I'm holding laser 2 at a fixed frequency, and I'm varying delta omega by varying the frequency of laser 1 very, very slowly. At the rate that this entire thing takes about a second or so.
Yeah.
But this is the asymmetry that reflects what happens to the electric field, because these are just the eigenvalues, and so if I just look at this equation, then the electric field varies as e to the some lambda t, where lambda is the eigenvalue.
Maybe I rephrase the question. When you try to
experiment, you can't separate these two electric fields from each other because
But maybe I pose it this way. See, the parallel between quantum mechanics and this electric field business is that in quantum mechanics, the resulting state can be written as a linear superposition of states. So linear superposition principle holds. In a similar spirit, I can superpose electric fields to get resulting electric fields. Now, the collapse of the vector space in the quantum mechanical side, I'm trying to visualize what is its analog in terms of electric field. What is the vector space has collapsed there. So how should I visualize it in the context of electric fields? And that is the question. That's the question I'm trying to pose.
Yeah. So that's a difficult question to answer because you're going from. So in quantum mechanics, when I'm looking at the norm, I'm looking at commutators. Here I'm looking at correlation functions. When you go from quantum mechanics to classical physics.
Yeah.
And so you're losing a lot of information in going from commutators to correlation functions.
Okay, so fine. I mean, I can say something about the degeneracy, but saying something more is going to be much more harder.
Yes.
And the other question is when you go around the exceptional point, depending on the order of the exceptional point. So I think the interesting thing is around it rather than exactly at it, that you have to circle twice or thrice to come back to the same eigenvalues and the eigenvalue exchange on the way. Do you have any way to actually do that experimentally? I mean, go around it and check this out, that there is a square root singularity or a cube root singularity there?
Yes. So that's a good question. So two remarks. Depending on what one's motivation is, sitting at the exceptional points is interesting to those who want to make sensors. Okay. Going around it is interesting for those who are looking at things like the Berry's phase and
Yeah, absolutely, yes. Yeah.
Now, so in this experiment, how do I go around? Okay, so as a fundamental point, independent of my experiments or anything else, is I need a third axis. Okay? Yeah. And in my case, that third axis is the time delay itself. It's that phase accumulation factor e to the I theta tau.
I see.
So by varying that, so for example, if I just naively say, okay, supposing I vary tau, that gives me a third axis. So I would have two axes. I would have lambda 1, lambda 2, and what is my third axis? The third axis would be tau. And if I can smoothly vary this tau, I can go around that exceptional point.
Oh, I see. So that's a nice handle for exploring that physics.
Correct.
I see. Interesting. And the last,
but good question. Yes.
Last point is, so for a non-Hermitian Hamiltonian, you have left eigenstate and right eigenstate. Now you have really a physical existence of this thing here. So what is the difference between the preparation of a left eigenstate and looking at its evolution, and looking at the image of it, the dual of it, which is the right eigenstate, which is not really Hermitian conjugate? So can you see this, check this out in the experiment independently and see that they are really image of each other in the PT-symmetric sense? Is it possible to do?
No, because the system is completely classical.
I see. So you only prepare right eigenstate. Is that what you're saying? You cannot prepare the dual of it. There is no way to prepare a dual of it.
Yeah, not in this case, because then one would have to really, it would have to be a completely different system, because I can't do this in this system.
I see. Okay, thanks a lot. Yeah, thank you.
Sure.
There are a couple more questions in the chat box, Gautam. Mm-hmm. The person who has asked the question about three-level system has also asked the question. This may be a very naive question, but I have come across the terms loss and gain many times. But what exactly is being lost or gained here? Is it information or energy or some other quantity? That's his question. And
the answer is yes, all of the above. So if I information, energy, these are all the same thing. But if you think of that waveguide example, then it's light that is being either amplified or lost. So that's energy.
And also information. You can also call it information.
Yeah. So,
okay. Yeah. And there is one more question. If there is a Hamiltonian which is PT-symmetric, can interaction with quantum channels make the system non-PT-symmetric?
So I need a little bit of help with this. What does the question mean?
I don't know. Maybe Sauren has to come in. Huh? If there is a Hamiltonian which is PT-symmetric, can the interaction with quantum channels make the system a non-PT-symmetric? Is it going to change the symmetry, PT-symmetry of it by interaction?
This is not my question. Sorry,
I know it's not your question, but I thought you might be able to help. That's what I thought.
Okay.
So does the individual mean that there is a dissipation? It's not.
I think that's
what the quantum channel. That's what he's asking.
That is what the body means. Yeah.
Prashant, you want to say something?
I think. Okay. I mean, perhaps the individual just means. Supposing I make the okay, so PT symmetry requires the diagonal elements to be equal, but supposing they're unequal, maybe that's one way to interpret this. And the answer is yes. I mean, there's now enough work to show that you don't necessarily need these diagonal elements to be equal to each other, because what really matters is what is the average of those two. So if I have I gamma and some I gamma prime, I can use the average of gamma and gamma prime as the point above which I have gain and loss. So it's just a matter of some translation. A linear translation, and then the system would go back to being PT-symmetric again.
His question is, will it become non-PT-symmetric?
Non-PT-symmetric.
That's what is the question.
I mean, the answer is yes, because the PT-symmetry would so it's not clear to me what the individual means by. I mean, does it mean the PT-symmetry is broken? That the eigenvalues become complex. Is that what is meant?
System is in dissipative environment, right?
So I'm a little bit not clear quite what the question is.
Yeah, Lakshmi, I have a question.
Please, Prashanta, there is one more here. Can I read it and you'll ask the question later?
Sure.
Okay, so Gautam, you have a lot of questions. Huh? There is one more question from Abhinash Roy. Thank you for this wonderful talk. The question is there any relativistic version of PT-symmetric quantum theory, that is PT-symmetric field theory? In this context, one relevant question is, for continuous real energy spectrum, can you surely say that the corresponding operator is Hermitian or PT-symmetric? Is the question.
So I'm not. I don't know if I can give a complete answer, but I think if the question is if the energy spectrum is real, I think that one can always concoct another effective Hamiltonian, which is neither PT-symmetric nor Hermitian, but which will still give you a purely real spectrum.
Good enough. Fair enough. Now Prashanta has a question. Prashanta, over to you.
Yeah. See, Gautam.
Yeah.
This there are these two type of exceptional points. One is when the two real eigenvalues coincide. One in the complex side, you have this zero energy, zero width resonance. If you take a PT-symmetric system in the complex side, there are these two complex eigenvalues coincide, and that is that zero width resonance.
Yeah.
Now, in your case, do you see any difference between from the real side when you have exceptional point and the complex side, the zero width resonance?
No. So so there's a bit of a complication because of this time delay. Our system is okay. So let me tell you how we do it. Then you will see why it is that we can't quite do what can't address the question you're asking. So what we do is we analytically solve for this critical detuning for which, let us say, 2 eigenvalues coincide and 3 eigenvalues coincide, whatever it is. But that is only we look for coincidence of the eigenvalues. Then we look at the corresponding eigenvectors and numerically determine the angle between them. Okay. So I'm not really looking at the real part versus the complex, the imaginary part, and then looking at their coincidence. So I'm not able to do what one can do for a zero delay system. But I think you raise an interesting question. I think it is it's something that's we have seen some numerical evidence of what you're asking, which is that the imaginary part coincides. But we had not paid too much attention to this because we were focused on these exceptional points of the conventional type. Okay, but that's interesting. We should talk about this.
One more question. There are some papers, 2019, there was a PRL paper that when you come from the real side, claim was that the photon stops at exceptional point. It was a standard Vemuri equation kind of analysis of the fiber. Photon stops at exceptional point. Do you see any change in speed in the electric field or no?
Oh boy, I don't think we can measure anything of that sort. I mean, I don't even know how one would measure something like that. You're asking about measuring the change in the speed?
That's right.
That would be, and part of the reason I would not be able to measure that is because I was giving this example of how the refractive index is continuously changing. So when I'm getting these transitions, part of what is happening is that the refractive index within the laser is continuously changing as those transitions are happening. So if the refractive index is changing, there is some change in the speed already. So how to separate that from other effects that may be causing any change? That might be hard to do.
Very good. Thanks. Very nice.
Okay, so Prashanta, I think Prashanta?
Yeah.
I think now the questions are more or less over.
Yes.
So we thank Gautam Vemuri for giving such a wonderful talk and making it simple and understood by everybody which is evident from the questions that have been fired. And thank you for making a complicated topic simple and reaching out to everybody. And I have understood it well. So the students who are the younger generation must have even understood it better than us. So thank you very much for a wonderful talk, Gautam. And it's nice seeing you again after a long gap, what with this COVID and all.
Yeah.
So let's hope you come back to India soon after these things ease out and visit us and ISER and, visit us again in India.
Well, thank you so much. I really enjoyed this, and I'm so glad you're doing this. I think this is I think it's really wonderful for your students.
That is true.
Yeah.
And Gautam, it is already nearing 9:30, and there are the number which I was looking in Zoom is gone to about 135 or something like that. So, you are doing good.
There are
106 people even for the question answer session also. So people are interested even at this hour of the day to listen to you. We are already hitting 9:30 here.
Yes.
I think Anantalakshmi, you have to do a controlled experiment. How many people would you get in non-COVID times when they can go out and they can go to a movie or go to a restaurant or something?
Actually, you are getting more people because of the COVID.
Yeah,
that's what I'm saying.
Gautam, that also for lectures. In the classroom, they make excuses. In the online classroom, they say they have digital divide.